Okay, so let's move to lecture 2, driving forces for mass transport. In previous lectures, we know that the flux of atomic flow can be expressed as negative diffusivity concentration gradient is based on Fitzgerald's law, and also can be rewritten as concentration of diffusing atoms, mobility of diffusing atoms, or also times is driving force is a negative chemical potential gradient. But however, if there exist other driving forces to drive mass transport except this chemical potential gradient, how to modify the atomic flux? For example, other force, for example, like electrons migration, which means that electrons flow to induce or push the atoms atomic migration or temperature gradient probably also, as long as it's large enough, it probably also can drive the atomic flow or capillarity or stress gradient. So in these lectures, we are going to show you there are four possible driving force to drive um, atomic flow or atomic flux. And the first part, we are going to introduce you your familiar one we call the diffusion in solid materials. And the driving force in this case will be the chemical potential gradient instead of the concentration gradient. The quite famous example here would be the spinodal decomposition. Actually, in this case, uh, the atoms at lower concentration regime moves to higher concentration regime, which demonstrates that the driving force is not the concentration gradient, which is chemical potential gradient. And as you learn or we proved in previous slide, we know that based on the chemical potential, we know that actually is changes with the concentration or atomic fraction XA. So if you have higher concentration, which means that you have higher, larger XA, and the atom will have higher chemical potential. Due to this reason, so atom A should tend to move to somewhere with lower chemical potential region. So that will drive this atomic flow, which we call a diffusion phenomena. And the second one, we are going to introduce you in the second section, we call the electron migration. Electron, which means that the driving force actually is the electrical potential gradient. So in the beginning, some scientists have found that under this electrical potential gradient, which means that you connect your materials with the battery, and we have the current passing through our materials. Under these situations, they find the positive ion running toward to anode under higher concentration, higher current density. They find some weird positive ion, for example, like metal ion with positive charge. They run toward to anode, which also positive charge is some kind of wheel, right? In our sense, would be a positive metal ion probably would tend to move to negative, right? Probably would be cathode, right? So this is how scientists find that it's weird. So they do more studies, find out actually the driving force to drive this positive metal ion runs to or running towards to anode with also positive charge is due to the is not due to the intrinsic electrical field, is due to the electrons wind or electrons flow to bombard on this positive metal ion to push this ion moves. So that lead this. So the moving direction should be identical with the electrons flow. So that's why um, let's explain why they observed the positive metal ion running toward to anode. So let me give you a quick draw. Uh, the positive, sorry. So this is positive metal ion. So when you connect with, sorry, with a battery, and this is positive, it's negative. So in most of cases, due to the internal electrical field, 内电场, you probably think that the metal should go this way. But our scientists observed that this positive ion is go this way and only happen in higher current density. So they find that actually the driving force actually is the electrons flow. So this is electrons. Because we have higher current density means that we have higher or larger electrons flow. So this electrons flow is go outside direction with this is a current go this way, right? So electrons will go this way. Okay, so this electrons will bombardment on this metal ion and push these ions move toward to these directions. So this is the results. This also can explain why they observe this phenomenon. So the driving force for electrons migration actually is we do have the higher current density caused by the higher electrical potential gradient. So that probably would lead the electrons bombardment on the metal, positive metal ion, and push them moves along the same direction of electrons flow. So this is we are going to explain this one in the second sections. And the third section we call a thermal migration. The driving force actually is a temperature gradient. As long as we do have a large temperature gradient, and this will also drive the atoms moves, okay? And also the moving direction we will discuss later. And the fourth possible driving force is we call a capillarity effect, which is due to we do have the curvature varying on our material surface. And the surface chemical potential varied in the meantime, so that will cause the surface chemical potential gradient. And this gradient, potential gradient, will drive the atom moves to somewhere with lower surface chemical potential sign. So that's what we call a capillarity effect. So the atoms on or at the convex region tend to um, move to the concave region with lower chemical surface chemical potential. And the last one we call a stress migration, and actually stress migration, which means that they have the stress field, right? So the atoms at compressive region tend to move to tensile region, and that also lead the long distance atomic transport. Okay, so how about if this is like we have 5 different driving force to drive the atomic flow, right? But how to deal with if there are 2 or more coexist in your system or co-acting on your material system? So we will introduce this. But give you the results first, you need to summarize all the chemical potential gradient and take the negative term, then you can deal with, because you already have a driving force, so probably you can write down the atomic flux. Why? Because atomic flux can be written as a negative mobility, concentration, and driving force, and this can be a summarized driving force. Okay, but the detail we will introduce later. Okay, so let's move to the first one. You're familiar with one. We call a diffusion mechanism. Okay, for the first one, diffusion, we will introduce you what's the relationship between the diffusivity and mobility. Both of them are the term you use to describe how atoms moves, how fast or how slow atoms moves inside your materials. But are there any relationship between them? And the following, we will introduce the we do have like based on the fixed first law, due to the different reference coordinates in our diffusion systems, people usually have three different kinds of types of diffusivity, including the self diffusivity, intrinsic diffusivity, and interdiffusivity. All of them are based on different reference coordinate and different material systems. And how to, or under what kind of conditions will you or use which one, and we will show you later. And the last one to like close the sections will be introduce the Kirkendall effect. It's a typical diffusion phenomenon happen in um, like materials, AB materials couple, which means that we use A materials bind with B materials together, and we have AB diffusion couple. We have a couple of materials. And when we heat these materials up and allow interdiffusions happens, then you can observe the void formation at one side and also observe the interlattice plane shift interface, the interface shift, then this phenomenon we call the Kirkendall effect. Okay, so let's move to the first one. Is what's a relationship between the diffusivity D and also mobility M? So we will start in order to answer these questions. We start from the definition. What is the mass transport in solid materials? Mass transport. So first come out from your mind, probably will write down the flux. The vector flux actually is a vector, so we use it is these arrows. So the flux actually was numbers of atoms passing through the unit area in per unit time. We call the atomic flux. Can be expressed as concentration of these diffusing atoms, and the concentration the unit is a numbers per unit volume times the velocity is a distance divided by time. So we have a J equals to CV, and this is vector as well. And also some due to the mobility you learn actually is defined the physical meaning for mobility is the velocity field per unit, the velocity per unit force, which means that when you apply a unit driving force, the velocity of this atom moves along or inside these materials. So based on this, we can use the force times the mobility to substitute or replace this term. So we got the mobility times driving force. And as you know, the driving force also is a vector. So we also can get the flux equals to mobility concentration driving force. So this is the equation you learned before, but you know that how it gets here. So mass flux can be written as a concentration of diffusing atoms, mobility of diffusing atoms, and times its driving force. Okay, so have you already have this idea, and we have a mobility here. So we got here, right? So next question would be the question I just asked you. What's the relationship between the mobility and diffusivity? Mobility is the velocity per unit force, and diffusivity, the unit is the area divided by time. So what's the relationship between them? Because you can use mobility and also use diffusivity to describe how the atoms, how fast the atoms moves inside your materials. But what's the relationship between them? So mobility which equation you learn or you remember related with mobility would be the one I just introduced to you, right? It's a flux equals to concentration, mobility, and driving force here is negative chemical potential gradient. And for the diffusivity, you learn this term from fixed first law. So it's equals to flux, atomic flux equals to negative diffusivity concentration gradient. So we want to know what's the relationship between the mobility and also the diffusivity. So the idea is, because if you take carefully, the flux are the same, right? So this equals to this. But in order to know the relationship between mobility and diffusivity, somehow if I can substitute this term in terms of concentration gradient, then I can get this and this, the relationship between them. Or I can replace this in terms of chemical potential gradient，也就是说，我可以，因为它们两个事实上是相等的嘛，但现在我如果想要知道它们两个之间的关系，我要么就把这个chemical potential gradient 用浓度去做置换，那它们两个一比较之后，剩下的就会是 D 跟 M 之间的关系，或者是我把这个 term 换成chemical potential gradient，其实是同样的意思。So I'm going to find out what's the relationship between the chemical potential gradient versus the concentration gradient, 对不对? Okay, so let's give you a quick review. We explained this before, right? You can write down the total Gibbs free energy for AB alloy, and also you can get the chemical potential of atom A by partial total Gibbs free energy with respect with Na. So you can get this mu A equals to mu A zero, pure chemical potential of atom A in pure materials, A materials, plus KT log XA. So I just use this, just copy these equations here. And this is I get. I have a chemical potential versus the fraction XA. But a fraction is correlated with concentration, right? So my purpose here is I try to express this in terms of concentration. So this is how the idea will be, because I know this chemical potential link with concentration, but not directly to a concentration. It's go to the atomic fraction. Okay, so now I write this down and copy this one, and here XA can be written as a concentration of atom A times the average atomic volume. But some people probably will ask, why, Professor, XA can be rewritten as here? So I use the unit, try to explain why we can do this. Do this like approximation trick. Concentration of atom A is the numbers of atom A in total AB volume. Right? This is a concentration. How many atom? This is total volume, and how many atom A you have is a concentration A. And the average atomic volume, I have average atomic volume A. So you have average atomic volume A times how many atoms I have. This part actually is a total A volume in AB materials. So you can do this approximation, can be similar or approximated with XA. So as long as you have this approximation, then, and the order is like this, then we can do further. We take a look on this and this term. Now I have the chemical potential concentration term, but what we have, we prefer to convert this in terms of concentration gradient. But let's have gradient term, right? So gradient means that I partial with distance. So I partial this equation with distance with a gradient. So I gradient this term. And this term I gradient as well, but mu A0 gradient. But this is the chemical potential of atom A in pure A materials. So this value is nothing related with distance. So after I grade it equals to 0. And KT is R constants. also nothing related with distance. Okay, and concentration probably were related with distance, but this term also average atomic volume is nothing related with distance, right? Which means that even you change the distance, the average atomic volume remain constant. So this is what we say nothing related with distance. So the only parameter probably related with distance is Ca. So we cover, so this term you can have a log Ca plus log omega, but omega is nothing related with distance. So take the gradient, got 0. So the only term I have is this term. So I have a kt log Ca and take the gradient on it. So I have a reciprocal Ca gradient of Ca. So this is the result. This result is quite important. So label it with like five stars because we always use this relationship in the following some deviations. And next, as long as I have this results, this is like I can substitute this chemical potential gradient in terms of concentration gradient. So I just substitute this term. So next is flux equals to concentration, mobility, and the driving force here, mu negative chemical potential gradient A. I directly substitute this term, use this term, so I can get the negative mobility because I use this substitute here, right? So I got the KT CA delete CA. So all I have is a MAKT and concentration gradient, and also the negative term. And I successfully to substitute this chemical potential gradient term in terms of concentration gradient here. So next, I just compare with, sorry, I compare with this with the fixed first law. So I can get the relationship between the diffusivity and mobility. So diffusivity equals to mobility times kT. So I get that the mobility is proportion to the diffusivity. And okay, so diffusivity equals to mobility kT, or mobility equals to diffusivity divided by kT, and this is the rate. This equation is quite famous. We call the Einstein relation. Okay, so when you find that this material, the diffusivity of this atom is higher and also is proportional with mobility, so mobility is higher as well. Okay,